turn your camera off. Okay, good evening, everybody, and welcome especially to our friends from SARA. I know some of you are with us this evening. A few announcements to make. First of all, next meeting is May the 28th, and we've got Wolfgang with us, presenting his observations from the observatory in Astrophilia. Saturday, May the 22nd, which I think is a week tomorrow, we've got everything you wanted to know but were afraid to ask about Spectrum Lab. Paul Hyde is going to run a training workshop on Saturday, May the 22nd. And then our next training workshop will be June the 5th, and that's part 2 of Python for radio astronomers. The autumn term program is coming together, and we will be meeting on the first Friday of every month, and that term will conclude with a Christmas lecture. So that'll all be, that's in the process of being confirmed at the moment, and we'll post that up as soon as we've got all the details ready. Okay, so tonight we've got one of our own members, Brian Coleman is going to share his thoughts on and his expertise with us on the H-line observations. So Brian, thank you so much, and over to you.
Okay, well, I suppose we start with the difficult stuff, and that's to share the screen, isn't it?
It's always a challenge.
It's always a challenge. Here we go. Any sign of a screen?
Yeah, that's working.
Right. Let's try the slideshow. Have we still got a screen?
Yep.
Jolly good. Okay, well, good day, everybody. I hope that what I'm going to do is to show you how that even with a fairly small radio telescope in the backyard, it's possible to make some observations of the radiation from hydrogen that give the observer a bit of an insight into the shape and motion of our galaxy. This is all very amateurish stuff, I hasten to add. It's all, most of my equipment has been, with the possible exception of the dish itself, has been made out of junk lying around in the workshop. I'm going to refer occasionally to we. It's not the royal we. It's a group of us who formed a little group called the Hydrogen Line Observing Group a few years ago, and we pooled our expertise in this project. Okay, well, I'm going to start with a very brief reminder about spectral lines. Of course, they've played a huge part in astronomy, allowing us to identify the elements present in the atmosphere of stars and even exoplanets and so on. A long history, and of course in the early days they were all only the optical ones that were observed. And just to remind us, I'm sure this is ancient history for most of the folk, but thinking about the Bohr model of the atom, incident energy causing electrons to jump from their stable energy state to a higher one, absorbing energy on a precise wavelength and then dropping back and emitting it on a precise wavelength. Most of these lines, of course, in the optical part of the spectrum, because that's where the Mark I eyeball operates. But of course, some of them are very obligingly present in the radio part of the spectrum. And the top of the list, of course, is neutral hydrogen, which is the most abundant element in the observed universe, and it very obligingly emits radiation in the L band, which is pretty easy for us to detect. Of course, it was first predicted by Hendrik van der Holst in 1944, and first detected by Ewan and Purcell in about 1951, and later, of course, the maps of the hydrogen in the galaxy were made and its spiral structure was revealed. And this is really what we're trying to do from the backyard, just to have a bit of fun. Of course, the precise mechanism that causes the hydrogen line emission is a little bit more subtle than the ones just described. And here, incident energy is causing the spin of the single electron relative to the single proton in neutral hydrogen to change to a higher energy state. And when it flips back to the lower energy state, it emits a photon very precisely on 1420.405, and I'll spare you all the other decimal places. Whilst this is only thought to occur once every few billion years for a particular atom, hydrogen is so abundant that there's plenty of radiation for us to detect. It's all fairly straightforward. So what do we need to observe the hydrogen line? And here I'm going to distinguish not just detecting it, but actually making some fairly useful observations to help us to understand the shape of the galaxy. And for that reason, I'm suggesting that we need an antenna with an aperture of 2 meters or more. And as with all radio telescope, bigger is better. Mine is 3.7 meters, and that's reasonably adequate. It's very helpful to have a tracking system. You could make observations using transit type scans, but you get along a lot quicker if you've got a tracking system and you can decide which pixel you want to observe. You need a receiver that can scan a few megahertz around 1420 megahertz, and that can log the signals that you're observing. And you need a good system of logging the data. And I think you'll find that the systems that I'm describing here are extremely basic, but they nonetheless seem to work. Of course, the antenna size doesn't just determine the amount of energy that you can collect, but it also determines the pixel size that we can observe. Again, bigger is better. But our 3.7 meter antenna has done a reasonable job. And I think you could still do some useful work with something down to about 2 meters. After that, I think it would start to get a bit, you get less satisfactory observations. That's the way to put it. Now, one of the main things you're going to think about on the system is keeping the system noise to a minimum. We all know about using low noise amplifiers and so on, but you've got to start even before that. When you think about the way you're going to feed the dish, how you're going to collect the energy without picking up too much ground noise. Now, the most usual type of feed that folk use is the QMAR type feed, which is this one lying on the ground here. But my dish has a focal length over diameter of 0.43, and a QMAR type feed would very fully illuminate the dish with the inevitable pickup of some ground noise from behind the dish, or a significant amount of ground noise. So I opted to use a dual mode type of feed, which slightly under illuminates the dish, reducing overspill. And if you like, it's prioritizing low noise over antenna gain. So that's the type of feed that I use on my antenna. Just to look at the structure of the thing, it obviously focuses the energy down into a probe, which you see here. And every effort is made to keep the length of cable between the probe and the low noise amplifier to a minimum. The probe sits in here, and actually that cable comes out and goes into the low noise amplifier, which is here in this box. The next bit in the box is a down converter, which converts the 1420 down to a fixed IF The reason for that is that I have a long cable run back to the indoor part of the system, and I don't want any strange artifacts introduced by the kinks in the cable and so forth. So we scan the frequency by sending the local oscillator up to this down converter, and the output is a fixed IF. This then comes down to this box of tricks here, which is the receiver. It's made out of pretty standard bits. The signal first comes into a programmable attenuator, which is only there to make sure that we're always sitting in the most linear part of the detector range. Then there is the IF strip out of something like a private mobile radio, which would have been FM in its day. But all I'm really using is the front end and the filter, which is about 15 kilohertz wide, 12 or 15 kilohertz wide, which is quite nice, gives us a 15 kilohertz frequency bin, if you like. Because the discriminator and FM detector have been removed, the bit of gain has been replaced with some dual gate MOSFET stages here into a detector, diode detector, and there's simply an op amp that goes into an A to D converter. Perhaps if I move to the block diagram, that will be more helpful. So we've come down through the feed, fixed IF, programmable attenuator, fixed IF, down converted to the usual 10.7 megahertz, bandwidth about 15 kilohertz, AM detector. Local oscillator is a programmable, what they call a programmable crystal oscillator, SI 570, and the whole shooting match is controlled by a PIC. The other thing connected to it, as you see, is an RTC real-time clock. That is because your observations are going to need to be date and time stamped, and it's best to have that happen automatically so you don't get it wrong when you're logging the data. If you want more information or more details of the technical side of it, then there is an online talk I gave to the UK Microwave Group, which you can find from the UK Microwave Group website, microwavers.org. It goes into slightly more detail, not a lot, and make a second apology for the fact that this is all pretty ancient technology. It was designed and built from stuff lying around in the workshop, and some years ago, if I was starting again from scratch, you will be amazed to hear that I would probably use software-defined radio to do the job. You wouldn't have guessed, would you? And if there's anybody out there who's keen to have a go, I'd be very happy to talk to them. So what comes out of the receiver setup looks something like this, a bit of a header that's got date and time in there and a few other bits of calibration nonsense. And here we see the frequency scanning in 10 kilohertz steps. And as you may be able to see on your screens, this is set up as a comma-separated variable stream. So the only really relevant bits are frequency and the detector voltage at this point. And that is simply fed to, in my case, an ancient terminal program, Hyperterm, which logs it away nicely. And if we were then to take that data and put it into a simple spreadsheet, we would end up with something that looks a bit like this when we're looking at galactic longitude 84, latitude 0, i.e. right in the plane of the galaxy. We would see the detector voltage on the left and frequency on the right. Note that the first peak is lower frequency than the other peaks at this stage. So the other thing to note on this is that when making an observation with this equipment, at any rate, it's a good plan to start well before there's any radiation from hydrogen and finish well afterwards. And the reason for that is that you can then put in a simple correction for the slope of the filter across the bit that you're looking at, which enables us to remove the system noise and other background noise, which we will do in a minute. Now, to make sense of the data we're collecting, we need to know, obviously, the time, date, and direction of the observation. And because the Earth is rotating about its axis, we need to know the latitude of the observatory. And because the Earth is whizzing around the sun at about 30 kilometers per second, we need to know the date where we are in our orbit. And all these factors introduce their own velocities, depending on the time and date and direction. And we have to correct for those and adjust them to the local standard of rest. And we can do this using the one of the VLSR calculators. So just a reminder, that is why we date and timestamp all the observations. Once we've done that, we can end up with a trace like this one, where we have now, I'll come back to the vertical scale in a minute, but the horizontal scale is now in velocity, reference to the local standard of rest. And you'll notice also that the order of the peaks has been reversed, and that's to comply with the convention that red shifts are positive and blue shifts are negative. Right, the standard unit for brightness is antenna temperature, and we can calculate this from the Y factor. That is the increase in signal above the system temperature, which we need to calibrate, and we need to get a grip with that. But as you see, we now have a scale here, VLSR along the bottom and antenna temperature as the vertical scale, and that's the standard. And you'll see on some of the plots I show you, there is a red line which I've overlaid. That is the predicted data for an antenna with a similar beam width based on the data from the University of Bonn. We'll touch on that again a bit later. So the data are pasted. I simply paste them into a spreadsheet which has got the various formulae in it. And if you need any of these formulae and also any other links I mention in this, there's a PDF I put on my web pages, which you can track down. The quickest way is to type my radio call sign into Google, and you'll find the home page, and you will find the PDF mentioned there. And the radio call sign is G4NNS, Golf 4, November Sierra. So down on the column on the left, we've got the frequency going up in 10 kilohertz steps. The next one is the topocentric velocity, the velocity that we actually observe in kilometers per second. That will get changed across to the right here into VLSR, the velocity reference to the local standard of rest. And for each observations of this fairly amateurish type, it's quite sufficient to do the calculation of VLSR once, and the factors put up here, apparently it was minus 25.99 kilometers by the look of it. And that's factored in to give us the velocity reference to the local standard of rest. Detector voltage here, the attenuation, which actually is, we don't use in my system. It's adequate to set it to a given signal level, and the linearity of the detector is more than good enough without having to change the attenuation during the middle of an observation. These columns here are to calculate the noise floor based on the noise level at the start and the end of the scan. And I assumed in my case that the noise, the filter response was pretty much flat, straight line, and not terribly significant, but it's useful to take it out. Here is the Y factor that we've calculated, and here is the antenna temperature. Obviously, the few little rogue negative numbers in there due to noise and so forth, but that results in a trace of this kind. Sorry, it always seems to be G long 84 and lat 0. It's because it's my favorite place to point the antenna, I suppose. No more than that. Regarding calibration, there are some useful calibration points. This one is calibration point S7, which is galactic longitude 132, latitude -1. And again, here I've overlaid the data from the University of Bonn data to see how my calibration looks compared to theirs, and it confirms that the system temperature T-sys is around about 50 Kelvin with the antenna arrangement I've got, the feed arrangement, low noise amplifier, and all the other bits and pieces that contribute to the T-sys is 50K, which I was very happy with. It's possible to do better, no doubt, but I was quite happy with that, bearing in mind most of the hardware came out of the workshop junk box, with the exception of the low noise amplifier, which is one of Sam Jewell G4DDK's very low noise amplifiers. So next we need to plan how we're going to make all these observations, and in radio astronomy from the backyard we're observing pixels one at a time. I know that some of the fancy professional telescopes can do several at a time, but we're doing it one at a time. So we need to decide what size pixel we can observe, and that's determined by our beam width. With a beam width of a 3.7 meter dish is about 5 degrees to 3 dB points, and you can make useful observations down to about 2 degrees. So we took the decision to make our observations in 2 degree steps. So we start by deciding the coordinates where we're going to make our observations, and the objective was to observe as much of the galaxy as we could. From the northern hemisphere here, we can't see into the center of the galaxy, so I think our observation started about 20 and went around to 200 degrees. And you quickly find that the galaxy is amazingly flat. It shouldn't really surprise us, because when you look up the Milky Way, it doesn't subtend very many degrees. And we made the decision to observe in roughly +12 to -12 degrees of latitude, and in 2 degree steps, moving around the galaxy, the part of the galaxy that we can see. This slide simply says the same thing again, so I won't dwell too much on it. When we're planning our observation, one of the first things we've got to do is, my tracking software doesn't speak in galactic coordinates. It speaks in celestial coordinates, the right ascension and declination. So we need to convert the pixels that we propose to observe into celestial coordinates. And this is one of the online converters that's available to do that. Excuse me. So this part is probably a bit tedious, but if you can see this spreadsheet, we've got longitude coming along here, and the latitudes, some, not all of the latitudes that we're going to observe here. And in each cell, I have manually put the celestial coordinates of that particular pixel. And that's what we got to enter into the tracking system before we start making our observations. Okay, I don't think that slide's particularly helpful at this stage, so we go to the next one. So when we're in the observatory, or those of us who are radio amateurs would like to call it our shack, this is what appears on the screen. In the background is the plan, plan for observing the pixels we want to observe. In the front, this is the tracking software I use. It's homemade, but with a lot of help from various people. And as you see, one of its options is it speaks in right ascension and declination. So that's what we have to put in. Coincidentally, the other things it does is it will track the moon and the sun. The sun's useful for calibration, and the moon is because I do EME for amateur radio purposes with the dish as well. It's not a very particularly clever tracking system. It updates the dish position every 10 seconds, which is more than good enough for the hydrogen line. But I do EME up to 24 gigahertz, and you do need reasonable update rate for that. So that's what's on this half of the screen, and over on this half is the hyperterm simply logging the data that's being sent to it from the PIC. I'm going to go back up to the slide before just to remind, let's think about that, yes, this one. So the data comes out, gets pasted into the spreadsheet produces this kind of a graph for each pixel. Because the data can be presented in a variety of different ways, and this is one of the early ways that we started presenting the data. And you can see the various peaks and so on emerging. Members of the group who were far more adept at the graphics than I am managed to produce other ways of presenting the data. And here you can see, this is actually, this peak along here is the local hydrogen in our arm of the galaxy. And you can see hydrogen in another arm of the galaxy here that's just petering out. We're looking at galactic longitude along here, and vertical scale is antenna temperature. And here you can see something else is going on. There's something merging or with our arm of the galaxy. Here is one where we're looking around a constant galactic longitude, but we're looking around in latitude. And again, there's the big peak at 0 VASR, which is the hydrogen in our arm of the galaxy. And you can see that it quickly fades away as you look out of the plane of the galaxy. And over here is one of the other arms of the galaxy, which quickly disappears because by parallax, it's further away. And we can start to get a grip on that from the data we're collecting. I've really limited the amount of graphics I'm showing because I think it's an area where there's a lot more work to do. We kind of, the Hydrogen Line Observing Group, just sort of came to a bit of an end for various reasons, but there's no reason why it couldn't be fired up again if anybody wants to do some more work on the graphics. And here are some thoughts that I simply threw out. This one is a very crude, this is my idea of graphics, so you can see it's extremely primitive, my limited skills in that area. But this is our arm of the galaxy, that's long latitude 0 going all the way around. And you see from it how thin the galaxy is, a couple of interesting bulges appearing there. This is at longitude 90 to 70. It would be fun to explore that in more detail. I've cheated here, obviously, by taking data from the Bonn survey, because I can't see into the center of the galaxy and can't see the stuff that can be seen from the southern hemisphere. Another thought is producing an arrangement like this, where I think the distances, the horizontal distance, if you like, have been made by signal strength or an antenna temperature, and the others show the angles that are subtended. I would rather like to see somebody analyze this data in much more detail and be prepared to use a bit of artistic license, because after all, there is a great history of art in radio, in astronomy, optical astronomy at any rate. And I feel that we're also sort of computer bound, that we find it very difficult to bring that kind of thinking to some of the data we collect. And the next slide I'm going to show you, which is moving on to the measurements of the velocity, but it draws on something which is purely an artist's impression after all. And I'm sure we're all very familiar with this one, which is, of course, an artist's impression from the NASA data. It's something that we used during our observations to give us a distance scale, which was very useful. We could resolve the, from a large number of observations, you can start to tell which arm of the galaxy it is, corresponds to which peak in the in our data, simply by following the data around and seeing how they behave in the graphical sense. You can identify which peak belongs to which arm, and we can also determine the velocity and the orbital velocity of each section that we're looking at. And when you start to do that, sorry, going the wrong way. This chart has a scale here of velocity on the vertical scale and distance from the center of the galaxy on the bottom scale. And then behold, it produces a rather flat looking graph, which is rather troubling, because we know that that as you get further away from the center of the galaxy, the velocities should go down. They shouldn't stay the same. That's the way the solar system behaves. There is the Keplerian decline in velocity as you get further away from the center of mass. And of course, this is rather troubling and gives rise to the need of an explanation. And that is that we need to think about dark energy and dark matter as the reason why there isn't the Keplerian decline that we were all expecting to see. So I thought it was rather neat to end up by, in our efforts with the Hydrogen Line Observing Group, that we could sort of demonstrate the need for such things. Well, that's really all I've got for you for the moment. If you've got any questions, be happy to try and make up a plausible answer for you. So back to you, Paul. You're muted, Paul.
You're quite right. Well spotted. Yeah. Yes, here we go. Look, unmuted. Brian, Do you have any plans to upgrade the electronics to move towards SDR, RTL SDR?
I am very seriously tempted, but the main thing that's stopping me is I'm starting from a very low point on the learning curve. I'm playing with SDR at the moment, doing some stuff looking with meteor detection and things, which is just a lot of fun. And I'm on the bottom of an extremely low learning curve, and I'm sure that there are skills out there that far exceed mine. I would be happy to work with anybody who's going along that path. I think my skills, if any, are probably more in getting the signal into the software-defined radio than they are with designing the software-defined radio itself.
Yeah. Yeah, I get the feeling in the group from comments and mails that I've had that there's a number of people who are just embarking upon software-defined radio, and I'm sure there are those in the group as well that are have a lot more experience.
If you want to come to my Python session, we'll be doing RTL SDR and using Python to do the 1.4 gig sampling. So you get a taster of it there.
Sounds good.
You're quite welcome.
I'll be very interested in that.
Paul, if I can make a comment on the benefit of using SDRs. When you use a scanning receiver, like Brian has been doing so far, what you're doing is you're looking at part of the spectrum at any point in time. So you're scanning. So at one point, you're looking at something like 15 kilohertz of bandwidth, and then you're moving after a while to the next 15 kilohertz of bandwidth. So your signal to noise ratio will depend on the dwell time on each part of the spectrum. Now, the big benefit of using a software-defined radio is that it looks at the total spectrum all the time. So let's say if you had take 5 minutes to record a spectrum in a scanning receiver, you will get for each part of the spectrum a certain percentage of that 5 minutes of integration time. Well, with a software-defined radio, you get the full 5 minutes of integration time for each of the frequencies. And that gives a very substantial increase and benefit in the signal-to-noise ratio. And that's why I would, I mean, I fully understand that, and Brian has explained that if you had started at some point in time, a scanning receiver was the way to do and the way to go. And these times, as software-defined radios have become so, let's say, cheap and easily usable, that's really a great benefit, and you would probably see a substantial increase in the signal-to-noise of your spectra that you are getting.
Absolutely, I couldn't agree more.
Yeah, the point there is the software side. So how do you get? I mean, buying a software-defined radio is easy these days. There's there are a lot of options available at different price tags. And the software side, how you get the spectrum into your computer and how to do that. I'm more than happy to help with that. So if you want to go that path, just contact me and I can provide you probably with a almost turnkey solution to do that.
That's great. Very, very much interested, yes.
Maybe I have one more comment on the question how to deal with the coordinate conversion and the VLSR correction. These days, you mentioned some of the online calculators, and that may be a bit tedious, so you have to enter the data for each of the positions that you want to do. There is a very comprehensive package, which is called AstroPy, and maybe in one of the sessions on the Python, it would be worth dealing with that. And AstroPy has all these routines available for both coordinate conversions and also for doing the VLSR correction. So anybody who wants to go that path, I would recommend to look at AstroPy. And
That's a good idea. I'll make sure I introduce people to AstroPy.
yeah.
That's a
Yeah,
good
the
idea.
trouble is with AstroPy, it's an extremely comprehensive package, and many of the things that are incorporated there are more intended for the optical astronomy. But coordinate conversion is something which is definitely very useful for everybody who's doing radio astronomy.
Thank you. Any other points anybody would like to raise?
Yeah, I would ask a question. I assume you can hear me.
Yes.
I'm very much at the beginning. I'm optical. I've got a 12-inch RC up there, but I'm very interested in going into radio astronomy. I've got an SDR, and I've set it up with some LNAs and a filter at the antenna, and using the SDR back at the computer. And that's what was recommended on some of the websites I saw on the internet, rather than using the IF and moving the SDR up to the antenna. Is that such a benefit, or?
Well, I think the SDR route is the way to go. From a practical point of view, the SDR and the low noise amplifiers really need to be located pretty close to the antenna. And I think one of the things you've got to overcome is the, weatherproofing and so forth.
Yeah.
It needs to be out there near the dish. You don't want long cable runs, not just for the loss, but for the various strange artifacts that they will introduce, although you could calibrate them out maybe.
Right, okay. The other question I've got, and I realise now that I'm in a different league. My antenna is slightly smaller than yours. It's that big. Now that's 17 dB gain. It's a Wi-Fi antenna tuned to 2.4. Now I would like to use that. I assume it's going to be useless. But is there any way I can retune that to 1.42?
Not knowing the details of the antenna particularly well, I mean, there's always hope. But a small antenna like that, I think you will, even with a good conversion on it, whilst you may be able to just about detect hydrogen line radiation, the pixel size will be so enormous that you won't be able to sort of extract any useful observational detail from it. That's your problem.
I mean, I'm limited by the size of my backyard, which is a yard. I certainly couldn't put a 3-meter antenna up in it.
I don't know if Alan is listening. He built a hydrogen line telescope, a slightly bigger aperture than that, but I don't know. Have you still got that, Alan? And you had some reasonable results with it, didn't you? I don't know if he's got his ears on.
Roger, I think the antenna that you've shown is something that I have looked at and which is also used by Sarah as what they call scope in the box. Now, this antenna is originally intended for Wi-Fi, and I had looked at it with a network analyzer and said, no, it's not going to work okay. And then I put it out and put an LNA on it, and sure as hell, I saw the hydrogen. So it's really amazing. I can only encourage you to use that antenna. And I'm inclined to say, just to see that there is hydrogen, anything short of a wet shoestring will work. We have demonstrated the reception or the hydrogen with just a simple dipole. But again, as Brian pointed out, that won't give you any detailed information. You will see hydrogen is there, and as the let's say the galactic plane passes overhead, it will increase and will decrease after that. So I would say it's a good start, just to get acquainted with software-defined radio and how things work.
Yeah.
And to whetten your appetite to get to a larger dish eventually, and then do things like Brian did, looking at the details and the structure of the galaxy. But and definitely, Roger, I would encourage you use this antenna. It's going to work.
Yeah.
You'll definitely see the sun. You can
Yeah,
see it.
that's-
Really,
Yeah, you will, and you will see hydrogen.
Yeah,
Yeah,
that's
so-
one of my interests, because I do a lot of optical imaging of the sun in hydrogen alpha, and I'd like to be able to see the prominences and flares coming up in the radio side as well.
I think just to point on this, a really good way forward is that Neil was mentioning his wonderful site up there, up north of Cornwall, long way north of Cornwall, and I think the possibility of getting various clubs around the country who have got access to a bit of land in an electrically quiet area and who could put up a bigger antenna and making it available via the internet, that's the way forward, would allow a lot of people to make useful observations. We did a little bit of this with the Hydrogen Line Observing Group. In fact, we had people from as far away as Chile controlling the telescope just by very simple, crude means of using, we used go-to meetings and passed control of the computer to the person making the observation. So, you know, I think there's a lot that could be done collectively by tapping into the locations that some of the optical astronomy groups have got.
Just on the subject of the antenna, it's I've got a few slides I can show if people would like to see them on my setup, and I've got a 1 meter dish, which was somebody had junked basically, and I've got some some nice results out of that. So yeah, you don't have to have a big antenna, and if your space is limited, it can just be a temporary setup. You can do your observation and then put it away again.
Yeah, that's right. That's what I do.
I presume that a 3 meter dish is too small to be able to see Andromeda.
I haven't made any very serious efforts at looking at Andromeda. I would imagine you can, but I don't think it'll be, you know, bigger is better.
Yeah.
Well, I remember
was desperately trying to remember how strong it was.
Well,
No.
I've seen the result from Jean-Jacques in France. He has a 3 meter dish and he has observed Andromeda, and he had I think similar system temperature like you, Brian. By the way, Brian, I think your 50K is really very good. That's certainly a well optimized dish, I would say, in my experience. And as far as recall, Jean-Jacques in France, he has 40K, and that's the best 3 meter dish that I have seen in terms of system temperature. And he has seen Andromeda, maybe even in yet another, I don't recall which galaxy, maybe another galaxy as well. So it's doable with a 3 meter dish if that is well optimized.
Yeah. Okay.
I have a question. It's a kind of a beginner's question, but I too have a small dish that I want to play with later in the year, a 1 meter dish with SDR, but I'm just a bit concerned about the detector, the feed, because with such a small dish, does it not cast a shadow itself, shall we say, on the dish? How do you
Blockage, yes.
how do you solve that problem with such a small dish?
Well,
I mean, like the Wi-Fi one, for example.
Yes, I mean, it is a fundamental problem of blockage, unless of course it's an offset dish. If you can find an offset dish, that's if it's a small dish. Of course, a lot of satellite dishes are offset. Then you don't suffer from blockage in the same way. So look at, rather than a prime focus, if there's a choice, find a one of the bigger sort of domestic satellite offset dishes. That's got to be a better bet, I would think.
That's the top I have.
Paul, can I share my screen for a second to show a small dish?
Yes, let me just switch that on again. I turned it off a minute ago, actually. Share screen is on. You should have it now. Yes.
You're muted.
Oh, sorry.
Yes.
This is a 1.20 meter dish. It's on a trailer because we use it to go to schools and observe hydrogen with schools. And that's a fairly flat dish. It's an F to D ratio of 0.5, if I recall correctly. And we're using just a coffee can feed there. Yes, you get some shadowing. On top of that, we have the LNA there. So you get some shadowing, but it's perfectly adequate to see the hydrogen spectrum and to see the rotation curve of the galaxy in a coarse way, but it's that is sufficient.
Interesting.
Paul, would you like me to show a few slides that I've put together?
Yes, you read my mind, Tony. I was just about to cue you in. So yes, go ahead. You should be able to share your screen.
Right, okay. I should be able to share my screen. So I'm going to share on screen 2. So just does that come up?
Yes.
Yeah.
Right, okay then. So I started messing around with astronomy for a long time ago. I played around with conventional electronics and radio telescope type stuff with limited success, it has to be said. The SDR has changed all that. So my arrangement is it's an RTL SDR version 3, which is you can get for about £30 off the internet. Homemade digital filter. I've used a couple of this is going from the SDR all the way through to the dish, so it's a kind of reverse order. A couple of cheap LNAs, which I found to be really good. They're very cheap. They're about £3 or £4 each. An expensive mini circuits LNA, but I think I might get one of the Sam Jewell ones. Actually, I think it probably looks like a better bet from a noise figure point of view. I use a coaxial relay, which has got an internal 50 ohm load, so I can do like a dark frame or a calibration with that to kind of get a baseline and then subtract that from the observations. A homemade bi-quad feed and then a surplus dish that somebody just dumped in the lane near where I live. So it's a very simple setup really. And I use SDR Sharp at the moment. And there's loads of information on that RTL SDR website. So that's my system diagram, which I think I've just described, but a homemade bi-quad dish feed I found to be really quite satisfactory for what I've done so far. But I've done none of the calibration that Brian suggested. So perhaps if I calibrate it to calculate system noise, perhaps it'll point the way to doing something better. But that's the basic arrangement. And then this is a picture of my dish, and it's as I said, a surplus dish which is just mounted on a little tripod. At the time I was powering it using some batteries, but I've then got a USB cable that goes to my laptop in my workshop here. But I've got the LNAs and relay and everything filter in this little box here, the RTL SDR in line there, and then the USB going away. So there's a bit more detail on the bi-quad feed and the interdigital filter. This is the bi-quad feed, so it's just a bit of aluminium and then a bit of power cable. I've stripped the insulation off and just mounted on an SMA socket that's bolted into the aluminium tray here, and then that's just held on a simple mounting. And then my filter is a interdigital filter in in a mint, one of these kind of mints they are, but I've got a strong mint box, little tin box, and they're bits of brake tubing, the sort of flexible stuff you use for replacing brake lines in a car, and that's just held in the box with some 50 ohm taps. It seems to work pretty well, really. There's a couple of links to the for the calculators, the online calculators that allow you to calculate the dimensions for these for 1420.4 megahertz. The first results, this is in December last year. So I've got SDR Sharp running on my laptop, and it runs this little plugin called IF Average. Now, it's a bit flaky, I have to say. It sometimes crashes, but you can set it to do an observation for, say, 5 minutes, 10 minutes, 15 minutes, or whatever. And it does many, many thousands of scans, and then it'll average them, and then you can get them to automatically write it to a file. You end up with a series of files, and the way I arranged it, because of the beam width, I was taking it roughly every 15 minutes. But that's an example of the hydrogen line. Now, I've not applied the velocity correction, so that's just inferred velocity from the Doppler shift. So I wouldn't take too much notice of the actual number, but it showed quite nicely that you get this profile. And then I did just at 10 degrees declination. Now this is celestial declination, not galactic, and a series of lines going through the night and then into the next day. I've not really had a chance, and I'd be very interested to join a call looking at how you process data, particularly in Python. I'm quite keen to have a go at doing all that, really. But the next step really is to run the SDR off of Raspberry Pi. And I bought a nice long Ethernet cables, and I could do power over Ethernet, so just one cable, and then I can have the radio telescope better placed in the garden. And I've got something so I can switch the dummy load in and out, just with a simple web browser. And I've got a little web server running on the Raspberry Pi as well. So that I've demonstrated it kind of on the bench, but I've not got around to actually getting any further to implement it yet.
That looks very good, Tony. Do you have an idea what the T-sys is?
I haven't calculated that, but I'd be interested to see how you do it, because but just looking at it by eyeball, I mean, it's obviously got a bit of noise. These are 1024 bins. So if I go back to the previous one, it gives you an idea of the kind of signal to noise ratio, but no, I don't know what the T-sys is.
On the Python, the next Python workshop, I'll be looking at RTL SDR using the Python libraries that are available for it, and there's a really nice library which does the calculation, or does the temperature calculation for you. You point you point it at a tree, and then you point it at some dark area of the sky, and then it does all the work for you. Seems to work, pretty simply. So so we can go through that if you come on the workshop. We'll cover that.
That'd be great, thank you. Anyway, I'll stop sharing, but I thought Paul just asked me to flick up what I've been doing, so I've inflicted it on you.
Thank you very much, Tony. Yeah, I found that very instructive. I'm going to go through this video again and pick up some of those websites and details. That's really good. I can imagine.
Paul, I'll send you the copy of my slides, and you can pass it on to anybody who's...
Yeah, anybody that would like them, do drop me a mail. I can just imagine a year on from now where people have been studying Python and getting into Matplotlib, we'll be having presentations that include all sorts of very fancy graphics of our data reductions. Can
I hope
highly
so.
recommend Rupert's Python course. It's kept me busy for the last 3 weeks trying to get my head around matplotlib. Oh. I think you might have a problem with your sound, Jack, or is it just me?
No,
No, you guys are
you
broken.
sound like a Dalek, Jack.
Dalek sound.
Oh, so sorry, we can't hear you.
Need interpretation.
Yeah, it's just not coming through, Jack. I'm so sorry about that.
I think it needs to reduce the microphone, I think.
Yeah, can you try just using the mic, Jack? Yeah. Yeah. Sorry, Jack. I just you're not connecting properly tonight. Do we have any more comments or questions regarding H-line observations and SDR?
Maybe just one comment. We've seen this interdigital filter just a few minutes ago with a reference to a website. There's another design for a hydrogen filter by the design is by Matthias Vidmar from Slovenia, and he's been using standard aluminum profiles. We have successfully used that. The benefit of that is that you just buy standard profiles and standard aluminum rods, and you, with very little mechanical skills, you can build such a filter. Unfortunately, I don't have the proper link, but Paul, I'll send it to you for further distribution.
If you would, that would be great.
Recommend.
Talking of filters, I used a 1.42 filter produced by, I can't remember his name, but it's the same guy who does the LNA for all. And that's just a small chip. And is it a CCL filter? I'm not too sure what it is. I was looking at it this evening. And that's just a very small chip. And I fit that in between my two low noise amplifiers, and then I also fit another one on the output of the SDR. Now I don't know how good it's going to be because I've not done anything with it yet, but I tried to manufacture the filter that we saw earlier, and it was fairly complicated design, like a copper box and everything. I produced all of that and it did absolutely nothing for me, so that's why I drew a line at that, and I bought the digital filter. But is anybody aware of those and their efficiency?
Yes, we have tested those. What I can suggest, if you go on our website, there is a series of articles about hydrogen line observations where we've tested various LNAs, where we've tested various filters and compare them. Again, Paul, I think the best thing is that I send the link to you for further distribution, where to find our articles on the hydrogen line observation.
Can I just commend you on your articles on your website? They're absolutely brilliant. And I fully intend to take a look at some of the other things like methanol, because that looks absolutely fantastic.
Indeed. Yeah, I second that.
I've just sent you that presentation, Paul, so yeah, pass it on to whoever wants it.
Okay, yes, I will do.
Got a question, Paul. Simple practical question from a UK perspective. Do you need planning permission for something that size in the back garden?
The size of a 3.7 meter dish, I did get planning permission, but I had something on my side, which was that it had originally been used for satellite, the development of satellite television, set-top boxes and the like, and it had got planning permission in the Peak District National Park. So there was one condition that it was that when he finished using it, it had to be removed, which is how come I got it. He had to get it removed and restore his little dry stone adit back to its original form. But when I applied for my planning permission, I said that it was for amateur radio and radio astronomy. And I got a letter back from them that said, what's it for? And I said, it's for amateur radio and radio astronomy. And they said, oh, well, that's all right then.
You could always make it a temporary structure, then you don't need planning permission.
The only snag with that is if you want to do anything else, like build a conservatory, they'll have you for that. That's the snag with bypassing the planning.
So build the conservatory first, is the
Indeed.
Thanks very much. That was interesting.
Very good.
Is there any more on this before I move on? It's been quite an exciting few days with the solar activity. And before we move on to that, I just want to make sure there's nothing left open or any questions for any of our speakers so far. No. Okay.
I'm going to have to leave you, I'm afraid, but thanks everybody for coming.
Thank you, Brian.
Very good.
Really good. Really good. Okay, I'm going to ask Mark if he'd like to share some of his very recent observations. Are you there, Mark?
Yeah, I'm here.
Ah, great. Yes, I can see you now. You should be able to share your screen.
Yeah, okay, I'll try. Can you see that?
Yes.
Yeah, I first heard about this. This was on the 12th from Roger, who runs the Mull magnetometer. And he'd said that he'd seen this magnetic impulse, and it had produced a traveling ionospheric disturbance that he'd seen on 23.4 kilohertz on the path to Germany. So I thought, oh, that's interesting. And it turned out it was a coronal mass ejection. And so this is the plot from the 12th, and I've got 4 frequencies here, and the top one is the path up to Skelton in the Lake District, so that's a northerly path. Then the next one at 20.9 kilohertz is a southerly path down to France. The bottom one is at 24 kilohertz, and that goes westerly to the east coast of America. And the one in the middle is the interesting one, because that's at 37.5 kilohertz, and that's the path up to Grindavik, next to the volcano in Iceland. And as you see, that 3 of them don't show anything particularly interesting. There's a lot of oscillation on the path up to Skelton, but that's been there for the past few days. But the interesting thing is the peaks you see at 37.5 kilohertz. And the impulse that Roger was talking about was coincident with this little peak at the beginning. And if I go to another plot, and this time I showed the 23.4 kilohertz path over to easterly over to Germany, I always find recently that this the amplitude of that signal glitches all over the place. And to my mind, these look like changes in the transmitter power because they're very sharp and they don't seem to have any relationship at all with flares or magnetic effects or anything. So I usually dismiss looking at that particular path because of this chaotic nature of its amplitude. And if you draw a line to see where this impulse was, the corresponding point that I saw on 23.4 kilohertz, nothing particularly interesting seems to be happening. There's not this wave that Roger saw from Mull. And of course, the path from Mull to northern Germany, the reflection points on the ionosphere, of course, are further north than they are for my path over to Germany, because I live down in the Midlands. So someone asked me, well, what does it normally look like? And it's been difficult at the moment because the sun has become more active, and what with transmitters switching off and a bit of lightning around, this was the best comparison I could find, which was from the 10th of May. So this is 2 days before. So you can see it's normally fairly flat. And if you look at the end, around between about 20 and 21 hours, there was a similar sort of glitching that you see here, these peaks. And so something happened on the 10th as well, which is similar to the occurrence on the 12th. Now, if we look at the time that Roger quoted, he said he saw this magnetic impulse at about 0638. And sure enough, this is my plot at 37.5 kilohertz. And the time where the amplitude increases is at 0638 and 12 seconds. So that really corresponds to this this magnetic effect. And obviously it's where the particles from this CME first collide with the ionosphere and lower it slightly. To get some idea of how strong an effect that is, later on, over at about 0935, we had the C-class flare. It wasn't a very strong one, it was only 1.5. And that produced a SID on a couple of frequencies. But on this frequency, it's buried in the noise. So you can see that the effect that these particles had was far greater than this C-class flare. Now, if you compare it with Roger's magnetometer trace, his is the 3 lines. You've got BX, BY, and BZ. And then the lower trace is my 37.5 kilohertz. The initial impulse he mentioned is here at 0638. But then later on, after 12, everything goes really crazy as the main bulk of the CME reached us. And the interesting thing is the very sharp rises or falls, if you like, falls of the ionosphere, but rises in the amplitude of the signal, correspond to sharp changes in the magnetic field. But the strange thing is sometimes there is a sharp change in the amplitude, which doesn't correspond with a change in the magnetic field, but in general, that's the case. There's a sharp one here just before 1500 that corresponds. And this is the sort of effect I've seen before, that these CMEs and changes in velocity and density in the solar wind only show up on the path to Iceland, whereas on the other frequencies, they go, to the east, west, and south. You don't see this effect. There was one occasion, though, which I showed in my talk from 2015, where the CME must have been so strong that it did show up on the southerly path up to Skelton, and that did produce one of these travelling disturbances like Roger has seen. But yeah, it's always interesting looking at that Icelandic path, and the volcano is spectacular as well. Yeah, so that's it. That's my my observation. I'll try and stop sharing if I can work out how to do it. There you go.
Thank you, Mark. It's always good to get current observations from our members. Any comments, anybody?
Yeah, Mark, you made some comments about 23.4 kilohertz being particularly unstable at the moment, which I see as well. Is that something you find comes and goes, or is it something new after the most recent maintenance? Because it was down for a best part of a month, and I suspect they've done something to it.
Yeah, well, say a year ago, it didn't do that, and I had a look at it today because I've had problems on 37.5 kilohertz because they'll change the modulation and just put a 50 hertz or 100 hertz test tone on. But looking at 23.4 today, when it changed amplitude, the modulation looked just the same. So I can only imagine it's deliberate, but it's only a recent thing, you know. A year ago, 2 years ago, it was fine. It of course always goes off at 7 o'clock for an hour, but besides that, it was fairly stable. Perhaps there were a loose connection somewhere.
Yeah, for me, today's trace looks like battlements on a castle.
Yeah, yeah. Oh, well, I compared it with yesterday, and some of the glitches are at the same time, not all. So there might be some hidden purpose behind it.
Thanks, Mark. Thank you very much. Does anybody else have anything they would like to share with us this evening?
I've just got a comment on the magnetic resonance measurements, the magnetometer, or what you call it. I saw a bit of the presentation about the American system a week or two ago. And that talked about burying things a meter under the ground, and I thought, gosh, I don't think I've got the facilities for that. And also the even with the BAA version, the problems with distance from roads and vehicles and moving metal objects and such like. And I felt that really I don't have a facility that I could do anything. I mean, how critical is that sort of thing?
Can I try to answer that? I've just started running one of the Eucra magnetometers, and I thought the same thing. Is this going to work? I put it in the shed. It's a suburban garden. It's probably about 100 feet from the house. When somebody goes in the shed and moves the wheelbarrow, yes, you see a spike on it, but by eye, it's very easy to separate that from what are natural phenomena, simply because of the way and the rate of change. So, you know, doing it by eye, I find it's quite an interesting instrument to watch. It is temperature sensitive in that if you put it outside and it catches this, for example, I've got mine in a sort of box outside the shed. In the winter, it's sort of reasonably happy, but in the summer, when the sun catches it in the afternoon and the temperature goes up, you can see the output changing. But again, it's pretty easy to get your eye in and sort them out by eye as to what's a temperature change and what's a magnetic field change. They do look completely different. So I'd kind of be encouraging to give it a go. I've found it very interesting, and say the next stage is to, can you stabilize the temperature or not? But I'm not quite sure to what lengths I'm willing to go in terms of either heating it in the winter or cooling it in the summer.
Right. The two systems seem to work fairly differently, and I wonder what's the benefits. Is there a benefit in one over the other? The sort of the buried sensors in 3 dimensions to the electronic circuitry version.
I just think there are different ways of doing very much the same thing.
Right. So the results are similar.
Oh yes, I would say I see the same kind of. If I look at the British Geological Survey magnetometer website, I see the same sort of effects at the same times. What I would say is different is it's difficult to relate the output of the UCRA magnetometer to the standard 3-axis coordinate system because of the way it works. But as an indicator of activity, it works fine.
Oh, all right, good. All right, thanks. We got that.
Yeah, I too have been running the UCRA magnetometer now for maybe 18 months. And I moved it from the an enclosure on the roof of my observatory into the back bedroom simply because of the temperature change. And in the house, I hardly notice any change in temperature, but it's very sensitive to any metal around, that's for sure, or movement of metal.
Yeah.
It's a magnetometer, I suppose. It's inherent.
Yes.
At least. Paul, if anyone's into, I'll just show what I saw on the other day.
Oh yes.
Share my screen. Share. That's the trace for the 12th. In the 2 axes, it measures. Yep, that looks like everybody else's. You can see the starting point at 6 o'clock, and it tracks it quite nicely. It's the most active thing I think I've observed since I started, and I'm quite pleased with that.
That's very good. Andrew, can you send me a copy of that? Because I'll be looking at my data when I get home from this trip. I'd be very interested to compare it with the same hardware.
Okay, I'll send you a copy.
Can I ask Paul how do you access the Python for radio astronomers? I didn't get to the first one, and I'd like to know how to get the second one.
Yes, there are three videos, and they're on the BAA YouTube channel, and there's a link to our playlist on any email that you've sent me, that I've sent to you, sorry, in my footer.
I shall have a look at that then, thank you.
Yeah.
I might join you on the 5th.
Very instructive.
I'll also send you a link. I'll stick a link in the chat to the GitHub site, which has got all the materials on it.
That'd be great,
Yeah, hang on, I'll do that now.
Virgo working, I don't know what I'm doing there.
For those of you that may not be aware, the chat, you can save it locally. So if you want to hang on to the link that Rue is posting, then if you go to the chat, go to the little 3 dots of more and save chat, then that will be saved to your local hard drive.
Oh, yeah. Clever.
Well, I will say thank you for tonight's little demonstration. One of the things that I'd like to make a comment about, I normally have been receiving on low frequency radio, but at the moment, owing to problems in the household, my aerials are not connected. I can see that I've missed a great opportunity. So that is a little bit disappointing. So you've given me the incentive now to get it all connected up and the area sorted out. So thanks for the encouragement for that one.
Hi to everyone.
Good night. Good night, Norman. I'm glad you were able to join us tonight.
Oh yeah, I've enjoyed it immensely. I'm not an active observer at the H-line. Excuse me. My hearing aid is squeaking. But
common problem.
by watching these Zoom meetings, I'm picking up the vibes of how things work. And one day I've got another aspect of radio astronomy to play with. At the end of the day, a lot of us are just little boys wanting to play with toys. So at that, gentleman and lady, I wish you all good night.
Yeah, good night, Norman. It's true to say that there's usually time on our Friday night meetings for anybody to share observations or bit of kit that they've got working, or these days bits of software that they've conquered. So do feel free to share, because there's huge expertise within the group, and there are also a number of us that are just embarking on this rather exciting journey. I'm going to close the meeting now, unless there's anybody that has got anything to say. I don't want to cut anybody off, but we don't need to extend more than necessary. Any final comments from anybody? In which case, I shall say good night, and we'll see you next time when we will be tackling the thorny problem of pulsar observations.
Oh, look forward to it.
With Peter East, I think. So, good night, one and all.
Good night.